Yeah, thank you for having me. Nice to see you all. My name is Richard Ghivhan. I'm the co-founder and the CEO of Haiku. I'm joined by our co-founder and CTO, Mykola. Mykola is his first name. Maskymenko is the second name. And we are really excited to talk about our work with HSBC. It was actually a nice preamble from Deloitte, consequently, because this work is relevant to CVAR calculations, so the calculation of risk via quantum Monte Carlo. This particular presentation is about the data embedding step, which is one of the main bottlenecks today, no longer. Before we talk about that, let me introduce you to Haiku, in case you don't know. So we are a quantum computing software company, and we're taking a very aggressive approach to practical quantum computing. We want it to be useful as soon as possible. The reason for this is simple. There are a lot of meaningful answers for society buried in a massive information that we need a quantum computer to recover, and we can't wait the 10 years for fault tolerance. Governments can't wait that long. Our investors can't wait that long. And so it means that we are put into this harsh reality where we're trying to make it possible sooner, and there's a few things you need to face. The first is that it's a long way away. Even if you have partial error correction, so long as certain types of operations, for example, non-Clifford operations, remain uncorrected due to high coding overheads, the computation is ultimately noisy. The fidelity of your computation will decay exponentially with the number of operations. And we're going to exist in this paradigm for as long as it takes to have full fault tolerance. Who knows, 10 years, maybe more, who knows. But you need software that can get enough depth on enough qubits to do something useful in the interim. And you need different software for different hardware modalities. And it's also the case that different hardware modalities are good for different things. You can think about it very simply. You know, for example, ion traps are super slow, but they have high connectivity. So if you had a simulation problem with long-range entanglement, they're a lot more effective for those sorts of problems. But perhaps you want to do quantum machine learning. In that case, you would want a superconducting device with a higher sampling rate. And it's even the case that for higher sampling rates, there are certain mitigation techniques that are more amenable to those devices. From the user's perspective, this is all a little bit inconvenient because they just want to run the application. So luckily for them, they don't need to think about which modality is best to route their problem to or which modality-specific software stack to apply, because that's what we do. And what we have is a software system. It's not a particular technique. It uses things you're familiar with, the hardware-aware transpilation, some proprietary error mitigation stuff. The real magnum opus of the system is an approximate circuit execution technique informed partially by condensed matter. You can ask us about it later. It's not the topic of this talk. But it ultimately means we can run super deep algorithms today, algorithms that are 100 times deeper. And functionally, what that means is certain applications that were thought to be 5, 7 years away are now about 2 years away at a practical scale. There's computational fluid dynamics and NMR spectroscopy that don't require too many qubits, but up till now are prohibitively deep. We're already running those applications at around 20 qubits at full depth. Today, we're more so talking about finance, which is what we work with our customer, HSBC, and especially about these problems that use quantum Monte Carlo or amplitude estimation. Of course, like the main bottleneck is you need to run amplitude estimation at scale, a deep, unwieldy algorithm. But there's another bottleneck, which is the data embedding step. You need to encode complex fat-tailed distributions. A fat-tailed distribution is just a wider distribution that accounts for unlikely externalities. These are hard to load, and up till today have not been loadable in an efficient manner at scale. Now they are, and oh my God. And that is what our co-founder and CTO, Mykola, will talk about today. So thank you very much. Let's give it up.
Thank you, Richard. All right, so let me continue. Loading data on the quantum computer is a well-known problem. It was out there for a while, and it's as important and as actually developing the quantum algorithms itself. And in the very direct way, it's actually one of the points of potential advantage, because we can actually load exponential amount of data on relatively few qubits. using, for example, amplitude embedding technique. However, the problem with this technique is that it produces exponentially deep circuits, circuits which require too many operations to run on any noisy device. So if you have some noise, you will be just killed by the accumulated error on each gate. So in practice, this was demonstrated only on very small qubit numbers, and we were not able to go to anything bigger. You can actually try to go around that using, for example, variational circuits. And with variational circuits, the idea is that you can try to learn that state instead of constructing the full depth. But the problem with that is, again, like if you move to the larger qubit numbers, it actually, these techniques becomes quite uncontrollable. And the error becomes also a little bit unpredictable, what kind of error you will get. And that's very much similar to what we have in like GANs in the classical machine learning as well. Recently, there was an interesting idea coming from more condensed metaphysics background on the using matrix product states classical data structure in order to construct efficient circuit representations for loaded data. And here you can actually end up with much shorter circuits, which are already on the linear depths, and that's already seems to be feasible for NISQ devices. And recently it was even demonstrated on few QPUs of the order of 20 qubits. However, if you go with these techniques to larger number, you can very quickly actually be killed by effects like instabilities of classically encoding this data on the larger tensors. Here we present a similar in spirit method developed by Haiqu, where we go beyond some of limitations of the initial matrix product states methods. We can construct now more controllable, very shallow circuits with a high fidelity of original distribution or data encoding. And moreover, what's very important, that now these are scalable to utility scale. So we can actually run these encodings on more than 60 qubits. That's what we tested, but we can scale that further. And let me now actually go into more details on that, but you can also find the paper which we just published yesterday. It's Bohun is the first author. You can actually find it on arXiv already today or look on our LinkedIn page. So in details, the idea of what we are doing here is the following. So we also start with tensor representation of data, but then we move forward by in-depth analyzing what the entanglement structure in that tensor network, and that informs us of what kind of circuit we need to decompose it in. And in the end, we actually can put gates only where they actually are needed, such that in results we construct very shallow circuits, actually in some cases more than twice shallower than previous approaches. And moreover, we can now scale that to a large number of qubits. So let's go into more details, like step by step, how it's being done. In general, we have two major steps. First step is you're having some data, having some distribution. We want to encode this in the tensor network form. And a second step would be taking that tensor network and decompose it into a linear depth circuit. In the first case, in the very standard approach, if you have, for example, a functional form of your data where you can actually describe it by some function of some argument x, you can actually discretize this x on some grid and using your qubits, and that will be a binary grid, very similar how you actually encode floating numbers. And in this case, different qubits would represent different scale at which of the grid. And interestingly, after doing that, you basically end up with a large tensor which encodes your data, and you can do standard decomposition of this tensor into tensor network, where you will have a collection of smaller tensors which are bounded by virtual links. And when you actually make those links smaller or larger, in this case, you want to compress, for example, information, so you reduce the dimensionality of those links, and that allows you to use much less memory to encode that data. That's a classical step. That's a standard step people use, for example, in condensed metaphysics to simulate quantum states in the Hamiltonian evolution. Now we can move forward and try to construct quantum circuits which encode these tensors, but actually on the quantum hardware. And where we actually add a lot of novelty. So first of all, in our paper, we actually derive analytical results for exact entanglement structure based on the functional or data properties that you want actually to load into tensor networks. In the result, we see that the entanglement is not uniformly uniform across the tensor network. It very much depends on the variability of your function and the smoothness of your function. And sometimes you can have some qubits which are entirely in the product state, some other qubits are actually highly entangled. And that very much impacts of what will be the circuit that you want to decompose this tensor network in. And as a result, we construct these adaptive circuits which actually have gates only where they actually are needed. And that's a direct procedure. So we don't do any training or anything like that. So you get your data, you load it into tensor network, then you have a direct procedure to decompose it into the tensor network based on those analytical results on entanglement. Moreover, we can now go in and look at the fidelity of the encoding on the quantum computer of how much that circuit captures the original data that we wanted to load. And we found that this fidelity is actually very high. So we capture almost all the necessary information that we wanted to load. And here is just an example. So we see that this infidelity sometimes it goes to the 10 to the minus 3, and it kind of saturates as you start discretizing your function. We also tested on different types of distributions and using standard tests like Kolmogorov-Smirnov test or KL diversion test, where we see that we actually have very high quality of this distribution loaded on the quantum computer with very low depths of circuits. So as you see here, we have, for example, for 15 qubits, it's just 30 C0s. So it's a very tiny circuit. So it allows you now to think that, okay, that's a very shallow circuit where I load the data, I can still load my algorithm now and execute something on that. So let's look how it works in practice, and I'm here very proud of talking about what we did with HSBC. So we approached the problem of loading heavy-tailed distributions. Just until recently, it was actually a very tough problem. There was almost no results in the literature of loading heavy-tailed distributions into quantum computer because typically you ended up with quite deep circuits, and it was very hard to control the errors there. As you can see on these plots, these are just some of the results from the paper. So we now can construct shallow circuits to load heavy-tailed distributions. Moreover, if you run them on the quantum hardware, you actually can pass the statistical test on the record breaking. Here it's 25 qubits. This was something that was not possible just recently. And in practice, that's very important for finance. Heavy-tailed distributions are all across different financial applications. They allow you to model different rare events which happens on the market. And if you want to do realistic financial modeling, you actually need to have an instrument how to operate with heavy-tailed distributions on the quantum computer. And now, when we can load the data and when we can actually construct these heavy-tailed distributions, we can now apply algorithms on top of that. And that's what we're working on now, and I can tease you that there are some very interesting results coming up very soon. So, but let me also outline something that is beyond just the functional form of the distributions. Suppose that you just have some sampled data, not in the form of a function, or you can have some use cases where you don't have a PDF, but you have a characteristic function of your distribution. So we have a method which allows us actually to tackle such use cases, and moreover, it now allows us to go beyond some limitations of standard tensor network approaches. And here is an example where we load, again, heavy-tailed gamma distribution with a high precision on the actual quantum computer on the 64 qubits. Just recently, to tell you, that was very hard to achieve. And here, as you see, we have all the good qualitative properties of this distribution, including the heavy long tail, and it's almost not corrupted by the noise of the device. So with that, let me conclude. So we have method which allows us now already today load different kinds of data in the very shallow circuits and run that at the utility scale on the quantum computer. I want to emphasize that this is not a single trick pony. So we can load different type of data beyond one-dimensional distributions or just financial data. For example, we currently experiment with some multivariate distributions and have already good results. We also applied it to the problems far beyond just financial distributions, for example, with some computational fluid applications, fluid dynamics applications. So the range of possibilities is wide. And if you have some interesting problem in your practice where you have challenge with loading some initial state or preparing initial state for the further running the algorithms, we are very interested actually to learn about it. So please approach us. These are LinkedIn, and we will be here for the next 3 days. Thank you.